students, welcome to the next session of Strength and Matrix 1. So in the previous class we have analyzed some members which are being symmetrical, and due to the application of some loads we have calculated the bending stresses, and using the pure bending theory concept we have came into the back steps like calculating maximum moment, and from the maximum moment we went into the loading condition, right? Now in today's class we are going into bending stresses in unsymmetrical sections. Firstly, what is an unsymmetrical section? Generally, in case of symmetrical sections, the neutral axis passes through the geometrical center. As we have already said, geometrical center means when we observe a section, the total depth divided by 2 will be the geometrical section line. Okay, so in case of symmetrical sections such as rectangular, square, circular or symmetrical eye section, you can observe this geometrical center line is the neutral axis line. Now, in case of unsymmetrical sections, what are those? Those are L, T and unsymmetrical I. Okay, so some sections which are unsymmetrical such as L, T and I. How they are not symmetrical? When you observe in L section, you can observe like this. Okay, so when you see any horizontal axis line, the top portion, bottom portion are not symmetrical. Or when you see any vertical, the left portion or the right portion are not symmetrical. So these two members are not at all being symmetrical about any axis. Similarly, for the T section also. When you observe a T section and about horizontal, the top portion, bottom portion are not symmetrical. But about the vertical, the left and the right are symmetrical. But when we are saying symmetrical section, that section should be symmetrical about horizontal and about vertical also. So the left segment and the right segment should be symmetrical. The horizontal down segment and the top segment should be symmetrical. Okay, so two axis symmetry should be there. In case of unsymmetrical eye section, maybe the top flange is having the different dimension than the bottom flange. The flange's dimensions may differ. So when we see the centroidal axis, the top portional segment and bottom portional segment are not symmetrical. But like the T section, the left segment and right segment may be symmetrical. Like T section, vertical symmetry may be there, but the horizontal symmetry is not there. Such type of symmetrical conditions we call it as unsymmetrical eye sections. Okay. So, in case of unsymmetrical eye sections such as L, T and unsymmetrical I, the neutral axis does not pass through the geometrical center. So, geometrical center means total depth by 2. That line is geometrical center line. Okay, so that is the geometrical center line and that is not passing through the centroidal line. Okay, so geometrical center line is not at all passing through the centroidal axis or the neutral axis. Centroidal axis and neutral axis are always symmetrical. So the sections, centroidal axis, sections, neutral axis are same, but geometrical axis will be there. That the geometrical axis is at total depth by 2. So at that when we give a line, so that line is the geometrical line and the geometrical center line is not coinciding with the neutral axis line or the centroidal axis line. And the neutral axis is passing through center of gravity of the section in unsymmetrical sections also. This thing we already know. Neutral axis is always passing through the center of gravity line or the centroidal axis line of the section. The value of phi from the top fiber is not at all equal to value of phi from the bottom fiber. See here, as you said, if it is a geometrical section, this and this will be equal. That's why this way and this way will be equal. But in case of centroidal axis line, because those two are not getting coincided, this y and this y are different. Geometrical center line will divide as equal depths or center of gravity will not give equal depths. That may be different, this may be different. That's why the height and this height are different. Now I am going into a problem with unsymmetrical eye section. Okay, the cast iron bracket being subjected to bending has cross section of eye form. Okay, so bracket means simply they are using like a beam. When any steel member I am using like a beam, I will say the word bracket. Okay, bracket section we call it as. Okay, so any eye-shaped section is used as a beam, so that only it will have bending action, right? So the bending, it is having a cross section as eye, and it is having unequal flanges. Unequal flanges. If they are mentioning like this unequal flanges, that means it is unsymmetrical eye section. Okay. Now the dimensions of the section are as shown in the figure. Okay. The unsymmetrical eye section, they have given a picture, and then find the position of the neutral axis. As we have already mentioned, this unsymmetrical eye section is having a top flange of 200 mm width and a 50 mm thickness and a web of 200 mm depth. Only web depth only they have given. In the previous conditions, maybe some overall depth they can give, or they will give the web depth itself. Okay. So depth of web is 200 and thickness of the web is 50 mm, and the bottom flange is 130 mm width and 50 mm thickness. So this is the overall eye sectional shape. In that, I need to locate the neutral axis. For neutral axis, locating the neutral axis means locating the centroidal axis only. When it is a symmetrical section, when it is uniform like a square, rectangle, circle or symmetrical eye section, the neutral axis is at overall depth by 2. Geometrical center line, neutral axis line, centroidal axis line, 3 are getting coincided. But in case of unsymmetrical sections, only neutral axis and centroidal axis are getting coincided, but the geometrical section line is somewhere different. Okay, the neutral axis line or centroid. Okay, neutral axis or the centroidal axis I need to locate. As you have already completed your engineering mechanics, you can locate centroidal axis for any sections, right? Centroidal axis location, y bar is equal to a1 y1 plus a2 x y2 a3 y3, like that we will calculate, right? So those centroidal axis location I need to do. And then what they have given, they are asking me to give the position for the neutral axis and also moment of inertia of the section about the neutral axis. So we have to calculate the moment of inertia about the neutral axis also. If the maximum bending moment occurring on the section is 40 meganewton millimeter, determine the maximum bending stress. So they have given capital M's answer. Okay, and they are asking us to calculate sigma max. What is the sigma max, and also what is the nature of the stress? Okay, they are asking us to calculate maximum bending stress and also the nature of the stress. What do you mean by nature of stress? As we have already said, a simply supported beam is having like this, and it will have compressive stresses in the top, tension stresses in the bottom. But in case of a cantilever, it will have tension stresses in the top, compressive stresses in the bottom, as the layers are getting compressed. Okay, so tensile stresses in the top, compressive stresses in the bottom. In this way, based on the beam condition, I need to give the nature. And in the picture, they have given it as a cantilever beam like this, and there is some loading condition. Okay, the load is not at all necessary because they have given the maximum moment. Only moment answer they have given, and they have given a section. So M, I, sigma, Y. Okay, these are the answers I need to know. And the maximum moment occurring onto the section, I know that they have given the problem. And I is moment of inertia of the section about the neutral axis. So for calculating moment of inertia about the neutral axis, first thing is I need to locate the neutral axis and I need to calculate the moment of inertia about the neutral axis. And then sigma max or sigma is the final unknown, and Y is distance of the corresponding point from the neutral axis. So these two will come at a time. These two we should have to give, and the first thing they have already given. So from the given data, capital M is equal to 400 meganewton millimeter. So 400 into 10 power of 6 Newton millimeter. Okay, so this they have given. Now observing the picture, I need to give the position of the neutral axis. So our step 1 is locating neutral axis. So locating neutral axis is the first step for us. Neutral axis always coincides with the centroidal axis of the section, as we have already know from the previous assumptions of the pure bending theory itself, and we have proved this statement also. Neutral axis is coinciding with the centroidal axis of the section. Now the distance of the centroidal axis from the base is equal to, observe the picture clearly, then only you can write what is happening. See here, this is my reference line. Okay, this is my reference line, and this is A1 for me, A2 and A3 for me. Okay, now A1 is there and A1 is at a distance of some Y1, right? A1 is at a distance of Y1 from the baseline, and also here A2 segment is there. This A2 is also at a distance of Y2 from baseline, and also A3 is there and it is at a distance of Y3. Okay, in this way I need to indicate. Later I will get what is the location of the overall central axis. A1 Y1 plus A2 Y2 plus A3 Y3. Area is being located at a point. That area locating point we call it as centroid. Okay, so area into the location of centroid of the A1 from baseline. Area into location of the centroid from the baseline. A3 into location of the centroid to the baseline. So these distances I need to write. And the first thing is A1. What is A1? 200 into 50. And the corresponding Y1. How we can calculate? Y1 is equal to, it is already 50 plus 200, 250 and total 50 by 2. So 250 plus 25. And then the next segment is A2 segment. That is 200 into 50 again. So 200 into 50, and that's Y2 is at a distance of 50 plus. Why 50 plus? This one is already 50. Okay, for me it is 50 plus this total height by 2. Okay, 200 by 2. 50 plus 200 by 2. And then the next area. The next area is the third one, that is 130 into 50. Only for the reference I am writing like 50 into 200 because B by D we will write, right? So 200, 50, 50, 200 and then 130, 50 like that I have given. And it was being multiplied with 50 by 2 because this 50 and at a distance of half of the 50 by 2. So Y3 is equal to 50 by 2 and divided by 200 into 50 plus 50 into 200 plus 130 into 50. Okay, A1 Y1 plus A2 Y2 plus A3 Y3 by A1 plus A2 plus A3. Now we have got the answer as 10,000 into 250 plus 25, 275, and then 10,000 into 50 plus 100, 150, 50 plus 100. See here, this one is 275, and that one is 150, and the last one is 25, which is 50 by 2. In this way, A1 by 1 plus A2 by 2 plus A3 by 3 by A1 plus A2 plus A3, we have got 166.51 from the bottom. So, overall I sections, as the I section is like this, and it is having an overall depth as 300 mm, and in that the neutral axis is being located at a distance of 166.51 millimeters from the bottom. Okay, as this is the overall depth 50, 250, and at a distance of 166.51 from the baseline, we are having the neutral axis or the centroidal axis. So, this NA or the centroidal axis line is like this. Therefore, the neutral axis of the section is equal to 166.51 from the baseline or from the bottom. Okay, that we have indicated here the overall structure, and that is third segment, second segment, and first segment. Or you can give 1, 2, 3 from the top to bottom anyway, no problem. And from the baseline, I have indicated. This indication is very important. You should have to draw this picture because they are asking for the position, right? So, this neutral axis is at a distance of 166.51 from the bottom. Maybe at some other time. From top also you need to write, right? So, the total 300 minus 166.51, that which is equal to 133.49 millimeters from the top. So, the neutral axis is at 133.49 millimeter from the top. And the top flange was like that and the bottom flange is like this. Okay. And we need to calculate moment of inertia of the I section about the neutral axis. Okay. And I am considering the first segment. As I am taking the top portion as the first segment every time. So I am taking this one only first again and again. One, two, three. Okay. For the first portion, that is 200 by 50 mm. And we are having the neutral axis like this. And the neutral axis is at a distance of 133.49 millimeters from the top. 133.49. Okay. So, this is the thing we are having. Individually, I am taking the moment of inertia. Okay. The first segment is like this. So, B 200 into D 50 cube divided by 12 plus 200 into 50 into Y means BD cube by 12 and Y means this measurement. For the corresponding I is equal to BD cube by 12 plus AY square. We will write like this, right? So, IXX plus AY square about any other axis which is not passing through the centroid. Okay? BD cube by 12 plus AY square. A we have written and Y. Y is nothing but what is this measurement? This one is 25 mm. So, 133.49 minus 50 divided by 2. That one. Removing this portion, the remaining 133.49 minus 50 by 2 is the remaining Y answer, and which is square. So, BD cube by 12 plus A into Y square is the moment of inertia of the first segment. And then for the second one, as the second one is the web portion like this, and it is having an overall depth of the web portion as 200 mm, and it is having the width as 50 mm, and the centroidal axis is located at, see here, this one is 133.49, or you can come from the bottom itself as this one is 50. So, 166.51 means 116.5. Okay. Now, about that axis, I need to write the moment of inertia of the section. Again, B is 50, D is 200 here. See here, what is the measurement which is parallel to the axis? That is B, that one is 50. And the next one is D. BD cube by 12 plus 50 into 200. Why I am writing this area? Because this original segment's centroid will be at 100 and 100, right? Original segment's centroid. Only for the web portion, the centroid will be at 100 mm. But I am taking moment of inertia about 116.5. So, this perpendicular distance between these centroids will be, I will write as y. So, 116.5 minus 100 whole square. Why that is coming? Because the original centroid of this web portion in the unsymmetrical eye section is not being coincided with the original centroid of the overall eye section. This web's centroidal axis is not coinciding with the overall eye section centroid. In the symmetrical sections, what is happening? Only the top flange and bottom flange are different, but the web's center line is coinciding with the overall neutral axis of the section. When you observe a symmetrical eye section and the centroidal axis of the overall section and centroidal axis of this portion are coinciding. That's why this A into y square term will not come. But here they are having the difference. That's why the measurement has come. And for the last portion, last is 130 and 50. And the neutral axis is at 116.5 mm. Okay, now for this portion B, 130 into D, 50 cube divided by 12 plus A, 130 into 50, and perpendicular distance of the centroidal axis from the overall centroidal axis is 116.5 minus, what is this distance? 50. That's my y2. A into y square. So, B d cube by 12 only for this portion, and the portion is at a distance of some y from the centroidal axis. So, distance of centroidal for the portion 130 by 50 and from the overall neutral axis. That measurement I have multiplied here. So, BD cube by 12 plus AY square, we have got the I3 answer. Summing up all the three, we will get overall moment of inertia of the unsymmetrical eye section. So, we have located neutral axis and we have calculated moment of inertia about the neutral axis. Now, we are going for the original calculation from the pure bending theory, that is equal to m by is equal to sigma by y. And when y is becoming y maximum, sigma will become sigma maximum. When we have just now observed y is having two different values, yc and yt. Why this yc and yt is occurring? As the cantilever beam is like this and the load is like this and it is causing bending. So, the top portion will have tension and the corresponding distance we call it as yt, and the bottom portion is having compression phase. The corresponding measurement we call it as yc. So, from the neutral axis, the top measurement is yt, and from the neutral axis, the bottom measurement is yc value. When we observe yc's answer, you will get sigma c. When you substitute yt's answer, you will get sigma t. And capital M, in the problem itself they have given, that was equal to 40 meganewton millimeters. We have already given as capital M 400 YC. What is those YCs and YTs? The values of these only. So, neutral axis to the top fiber I am having one distance. Neutral axis to the bottom fiber I am having another distance. Then you substitute the top portions where the tension is occurring. So, that is YT. Where the compression is occurring, that is YC. Substituting these two values, you will get 2 sigma answers with the substitution, and finally you will get the overall picture like this, and the measurement. This one is more as sigma is directly proportional to y. See here, sigma is equal to m by I into y. Like that only we have given, right? When we increase more y, you will get more sigma. As for this bottom only, y is more. As m and I are same. Overall moment of inertia are same. When y is more, sigma will be maximum. For the bottom only, the corresponding answer came compared to the top. In this way, we have calculated tension in the bending stress in the compression phase as well as in the tension phase, and finally we will give the nature. We are having the maximum tension is occurring in the compression phase only than compared to the tension phase in the cantilever beam. And we have indicated the neutral axis and we have given the values. In this way, we will conclude this problem. In the next class, we will calculate the strength of the section. Thank you.